Okay, so welcome to Teachers as Scholars Fibonacci's. This is the first lecture of the second half of the second day. All right, so I think this is lecture 7. And so what I wanted to talk a little bit about is efficiency.
The screen.
The screen is off. Thank you. I can see it fine. So let's, the TV might have
Went to sleep.
went to sleep. Yeah, so you probably don't. Okay.
Had a good lunch too.
Really good lunch. Okay, so we often, teach our students how to solve certain problems, but we don't worry so much about how long will it take to solve the problem. And as computers get better and better, this becomes, less of a worry. And I will admit to being intrigued as to where machine learning and artificial intelligence is going to bring us, in the next couple of years. Thinking every 2 years is a new generation. What do we want to be training our students to do? And so, did I share the table of integrals story in the first class? So when I was an undergrad, one of my professors told me, you have to have 2 tables of integrals, a small one that you keep on you at all times, and a big monster for your dorm room. Nobody uses table of integrals anymore. You do some kind of online program or program on your laptop or just some device. It's still worthwhile to know how to integrate, but you're not going to integrate anything too difficult by hand. So it's which techniques do we want students to know, and how much do we want them to know how you actually do it? And so maybe what I'll do is maybe I'll share one of the problems I'm actually going to be doing in my probability class on Tuesday. So yeah, I'll start with that. So is everybody familiar with the birthday problem? How many people do you need in a room before you have at least a 50% chance that 2 people share a birthday?
I've done it before, but I don't remember it.
Okay, so whenever you hear a problem, it's extremely important to think about what's not being said. So when I say, how many people do you need before you have at least a 50% chance that 2 people share a birthday? What implicit assumptions are there?
That there are 2 people in the room.
Well, that there's at least 2 people in the room. But what is
Some kind of distribution of the birthdays.
some kind of distribution? And what kind of distribution, since I'm not saying any, hopefully uniform. My wife is an identical twin. If we go to a family event on her side, there's a really good chance of at least 2 people sharing a birthday, right? And so one of the things is we assume that all the days are equally likely. There is a beautiful book by Malcolm Gladwell on called Outliers, where he looks at the distribution of birthdays in the Canadian Junior Hockey Championship game. And you see most of the names are on the first quarter, first third of the year. And the reason is when you're really young,
I was thinking it's specific to hockey and winter.
right, you want to be the oldest kid to just miss the cutoff.
Yeah.
Because when you're young, typically bigger kids are the older kids.
Yeah.
And so if you're bigger, you have an advantage. You'll typically do a little bit better. You then get more training, and it propagates all the way up.
Wasn't that the tipping point, the book?
I think it was Outliers.
Oh, wow.
Outliers, yeah. And it's just a wonderful example of how, I doubt that people born in the early parts of the year on average have better hockey ability. But the system unexpectedly created a structure that rewarded where you were born. And so it's worth asking, what kind of assumptions are we making whenever we hear a problem? So if you have around 22 people, there's a 50% chance that at least 2 will share a birthday. What I'm going to ask my students to do on Tuesday is to choose 2 days, 2 distinct days randomly in the year. What do you expect the separation to be between the days? And I'm not going to go wrap around. So anybody want to guess? We have from January 1 all the way to December 31. Anybody want to guess how much they expect the separation to be between the 2 days? So people are going to choose 2 dates at random, maybe March 1 and maybe September 22, or September 21. Any thoughts about what you would expect the separation to be? Can you give me an upper bound?
How many days are
Yeah, so say, so we'll just put it in quotes, right? That's what you do as a, whenever you're lecturing, you put it in quotes, so I don't worry, is it -1, is it -2? You're right that it's not as much as 365. Then we have to worry about February 29th, 365. Can anybody give me a lower bound?
0. No, it has to be two distinct different days.
2 distinct days,
So 1.
1. And there's no quotes on that one. We know it's at least 1. So any thoughts about where you are between 1 and 365? No wraparound. If you could wrap around, what would it be? It would just be a half. Where do you expect, if you choose 2 dates at random, how far do you expect the first one to be? How far do you expect the second one to be? If you were to just choose 1 day, where would you expect that 1 day to be? Smack in the middle. If you choose 2, where do you think the first should be? Where do you think the second should be? 1/3 and 2/3. So you might guess maybe 1/3 as at 1/3 and 2/3. And you can go through and you can actually prove this. It's not, too bad to do the algebra and the sums. And so I did it on, this is what a mathematician does. Whatever paper you have around you, you just happen to use. And I did it 2 ways. I did it both looking at just the average separation as well as the square of the separation. And so now what I will hopefully be able to do is, I want to take over and I want to share over here. All right, so hopefully this will pop up.
What do you mean by no wrapping around?
So for instance, January 1 is next to December 31 if you wrap around.
Rather than 365.
Got it.
Okay, so hopefully it's now showing. Okay, good. Now it's showing. Okay, so here, oops, is a quick computer program I wrote to do the calculations. And so I let spread be a list. Square of the spread is also a list, so I can measure things. And then year goes from 1 to D, so D will be 365. I choose randomly 2 distinct days in the year. That's what this line does. I then look at the absolute value of the difference between the two, so I don't have to worry about which one was the earlier one. And then I add that to my list of spread, and I add that to my list of spread squared, and then I just print out the values versus theory. And so when you look at it, so let's try the line. It should be compiled. And there's a link over here which takes you to a website where if you give it 2 days, it will tell you what the separation is between them. So you don't have to do what that is. And so now it's printing. Oops. Okay. Okay, here we go. So it's printing out the result and it's telling us how long it takes. And because this is highlighted, it means Mathematica is still thinking. Okay. And so the program takes a number here, which is how many simulations should it do. So initially does 10 simulations, then 100, then 1,000, and it keeps going on. The theory is 122 days, 149. It's a little bit off. But when I go up a little bit higher, 125 when I do 100, 115 when I do 1,000, 121.8 when I do 10,000, 121.9 when I do 100,000, and oops, and it's still running at 1 million. This program is taking a while to do. And so the problem is, why is this program running so slow? And so when you are teaching computer science or whatnot, there is a huge difference between theoretical mathematics and applied mathematics. It's very easy to factor a number. Just try all the numbers less than it and see what goes in. The universe will die a heat death numerous times before you make any progress. So you want to really think about, what is the computer doing? Is this a time when you have to code efficiently? And what I'm doing here is, I'm not solving necessarily the problem I want to solve. I am creating a list, and I'm storing all of the results in a list. So at the end of the day, not only will I be able to calculate the average, but I'll have all the data and I can do anything else. So if I want to do a lot of analysis, this is great. But if I only care about the average value, I am saving so much data that I don't need. The program is running slowly because it's creating this massive list, and I'm getting memory issues. So you really want to think what you want to do. If you really want to store all the results, what you should really do is you should have an array, and you just increment the value of 1, 2, 3, 4, 5 every time you have a separation of that. And now you only have to store 365 numbers. Whereas here now I'm storing something, 1 million numbers. So if I did it as an array, I would have all the same information, but in a much better way. I would lose the information about the order in which the days were randomly chosen, but nobody cares. So again, you really want to think about what you're doing. So what I then did is I modified the program and gave it the nice name fast 2-day spread, where rather than having them as arrays, I just had them now as numbers. And every time I ran through, I just took what I observed before, and I kept adding what I just observed. And then in the end, I just divide by the number of iterations. And so I'm not going to run it again, but this outputs the times of how long it took to run. So with 10 trials, it ran so fast mathematically, it couldn't even tell me how long it took. With 100 trials, it couldn't tell me how long. With 1,000 trials, it couldn't tell me how long for the fast way, but for the slow way, it did tell me it took 0.015 seconds. For the 10 to the 4th trials, it took about 0.03 seconds for the fast way, and it took 0.26 seconds for the slow way. Now, if you think about it, the fast way should be linear in the number of iterations I do. If I do an extra 10, because I'm just saving the result and incrementing, it should really be scaling linearly. The other one is scaling much, much worse. When I go from 10 to the 4th to 10 to the 5th, so when I go from 10 to the 4, it was 0.26, and instead of going up to 29 seconds. That's a huge increase. Whereas from the other one, I'm going from 0.031 to 0.375. That's very similar to a factor of 10 increase. It was much, much worse going up to 10 to the 6th. So much so that I got bored and just quit. I should really let the computer just run for an hour or two. But if it took half a minute to do 10 to the 5th, and look at the factor that we went up by like a factor of 100 it's just going to be terrible. And what I love about this is it's a great way to talk to students about the need to code efficiently. For a lot of things, it doesn't really matter. We don't have to worry. But just small tweaks in your code can make a tremendous difference. And when you're doing things in pure math, we often don't worry about this. We just say, oh, here's a procedure that will work. Okay, well, how long will this procedure take? I'll do one of my favorite examples, and then I'll shift back to polynomials. I don't think we talked the last time about the fractions that add up to 1. Is that correct? Okay, so let me go back and talk about the fractions that add up to 1. So I was at one of the top math institutes in the world almost 20 years ago, and you were given the following problem. Take the digits 1, 2, ... 9, and I want to form 3 fractions. Each fraction has a 1-digit numerator and a 2-digit denominator. And if you do it appropriately, you can get it to add up to 1. How many ways are there to place the numbers?
Place each number once.
Each number is used once and only once. Use each number exactly once. And again, it's not a multiplication problem, the denominator, that's just the number. So I could have 1/23 plus 4/56 plus 7/89. Anybody want to tell me how many ways there are to place the numbers?
Most 9 factorial.
So 9 factorial ways. And that's around 300,000. 6 factorial, well, let's see. 4 factorial is 24, 5 factorial is 120, 6 factorial is 720. And then 9 times 8 times 7, it's around 1,000. So 6 factorial times 987 would be at most 720,000, but 9 times 8 times 7 is not that big. 8 times 7 is 56 and 9 is less than 10. So this should be like a factor of 2 savings. Ballpark, I expect it to be around 300,000. Would you like to do 300,000 cases? No. How about your computer? Yeah, computer has no problem doing something 300,000 times if it's very straightforward. Now, we've done a lot with a few keywords. We've done shampoo mathematics a lot. But there's another word that begins with S that we've used a lot over the 2 days. Symmetry. Is there any way you can use symmetry to help you reduce the calculation? Without loss of generality, where must the 9 live?
In the first fraction.
Yeah, the first fraction. Because we can always reorder things. Right? If I have 3 fractions, it doesn't matter the order in which I add them. I can't say the 9 is in the numerator, but I can break it up into these 3 cases. It's the numerator, it's the 10s digit, it's the 1s digit. And I am extremely proud of the following fact. While my colleagues were proving theorems about where the digit 5 or 9 must be and impressing everybody with their mathematical powers, I decided to just write a computer program to do this. And I knew immediately that I could use symmetry to break it into 3 cases depending on where the 9 was. And I am very proud of the fact that I did not do that. Now, by now you should realize I love symmetry. Why did I not do this?
That much of a saved computation.
It's not that much of a safe computation. And how many times am I going to run this program? I'm trying to find the fractions that work. How many times do I have to run this program? Just once. This is not something that I'm going to be doing numerous times. This is a really good point to hammer home to students. If it's something that you're going to do a lot of times, it's worth spending a little bit of time thinking about how can I optimize? How can I do this well? If I'm only doing this once, I realized it would take me longer to code the 3 cases than to just have mathematically go through all 9 factorial possibilities. It was faster to be inefficient. And there is one and only one way to do it, up to reordering the 3 fractions. And I only have to run the program once. It wasn't worth doing it better. But if you're writing this for, say, a cell phone, and the cell phone is going to be trying to find ways to connect to nearby networks, your phone is going to be trying to connect to networks numerous times. Any little bit of savings you can get matters. So really think about what problem you're trying to solve. Do I need to be efficient? Can I afford to be a little bit inefficient if I'm only doing something once? Absolutely. And again, this is a point that's not emphasized nearly enough, is get a sense of what you're doing, what you need. And so, I love this problem. It's not too bad to code, but if you want to try to do this by hand, well, now all of a sudden, reducing where the 9 is to just 3 places, that saves you a factor of 3. It's still at 100,000 things to try, which is a bit painful. And then you start being an expert number theorist and start proving results about where the 5s and the 9s and whatnot can be. Sure. But initially, think about, do I need to do better? So what I want to do now is I want to talk about some math people have probably done all the time. So evaluating polynomials. Out of curiosity, how many people here have heard of Horner's algorithm? Excellent. So most of you have not heard of this. Okay. So let's say I give you f of x is, 6x to the 4th minus 3x cubed plus 7x squared minus 11x plus 2. In practice, you have to think of x as a really big number. Multiplication is much harder than addition. If I have 2 numbers that I want to add, the way you add is you add, digit by digit. And maybe you have some carries, right? But if you have 2 d-digit numbers, then the number of additions is on the order of 2d or 3d if you're doing carrying. So if I give you a 100-digit number and another 100-digit number, it's going to be on the order of 2 times 3 times 100. If I give you, it scales very nicely. For multiplication, it is much worse. So first, you would have this number goes to everything. Then you would have this number goes to everything, and so on until you get to the final one, which goes to everything. So the number of digit multiplications for 2 d-digit numbers is approximately d squared. Because when I have my 2 numbers, the last digit of the bottom number has to multiply all d digits up top. And then the second to last has to multiply all d digits on the top. And the next has to multiply all d digits on the top. I also have to add, but the adding is negligible relative to the multiplying if d is large. So for example, if d equals 100, multiplication is approximately 100 squared, while addition is only approximately 100. Addition is very cheap relative to multiplication. So I could ask, how many multiplications to evaluate f of x? So how many multiplications would it take to evaluate 6x to the 4th? How many multiplications do I need to find that term? So I need 6x to the 4th. Any thoughts? 5. Why 5? So x times, almost, x times x is 1. Times x is x squared. So x times x is x squared, that's 1 multiplication. Times x is x cubed, that's you're off by 1, right? So to calculate x to the 4th is 3 multiplications. It's x times x times x times x. It's 3 multiplications. And then the 6th is 1 more. So this would be 4 multiplications. How about 3x cubed? How many multiplications?
Or do it all from scratch.
Yep. 3 multiplications. And then the 7x squared, whoops, would be 2. And then I need another new color. Try this color. And this would be 1 multiplication. And so if we sum that all together, it would be 10 multiplications. So if you think about it, if I give you a polynomial of degree d, so we would write it as a sub d x to the d plus a sub d minus 1 x to the d minus 1 plus a1x plus a0. So this would be a general polynomial. And I just need names for the coefficients. I'm going to call the largest one AD to denote the fact that it is next to the term x to the d. So the number of multiplications, how many multiplications do I need for AD x to the d? D. It's d minus 1 to get x to the d, and then 1 more to get the AD. So it's going to be d plus d minus 1 plus 1 plus 0. And it turns out there's a really nice way to calculate this sum. If I let SD be the sum, d plus d minus 1 plus 1 plus 0, if I just write the numbers backwards, and I add, I get twice the sum. D plus 0 is d. D minus 1 plus 1 is d. 1 plus d minus 1 is d. And then 0 plus d is just d. By writing it backwards, I get the same sum every single time. I go from 0 to d, so I have d plus 1 term, so it's d times d plus 1. So the sum is just d times d plus 1 over 2. So this is order d squared. The main term is just some multiple of d squared. So if I want to evaluate a polynomial, it's going to take on the order of d squared operations. We did some fractals earlier today, and a lot of fractals take a polynomial and they keep iterating and they zoom in. And so when I was in high school, I wrote a program to draw fractal pictures and zoom in. And I wrote it in Pascal, which is not necessarily the greatest language, but it had fine graphics. The computer was not the fastest. And so every little bit of savings I could get, I needed. And this was not something that was being done once and only once. I was constantly reevaluating polynomials. So any savings would be magnified. So the question is there a better way to evaluate polynomials? So one of the things that often happens is we learn how to do something one way and we just keep doing it that way because that's what we first saw. Can anybody explain the word QWERTY? QWERTY, like a keyboard, Q-W-E-R-T-Y.
It's the way the keyboard is set up.
Why is the keyboard set up Q-W-E-R-T-Y?
Something to do with how you type.
Right, so it had something to do with, so why is the keyboard set up like QWERTY? But why are they choosing to put the letters there?
I mean, it had something to do with the frequency of which those letters are used.
Yes.
What fingers can
So
easily
what do
reach.
you think the
I
goal
never
was?
typed it.
So what do you think the goal was in choosing where to put letters on a typewriter?
Ease of access?
Speed of type.
Speed of typing. So what do you think this configuration is best at? It allows you to type.
More quickly,
No.
slower?
Yes. The QWERTY keyboard was designed to slow you down.
So you make
And so,
mistakes.
no, it was designed to have you alternating between hands and slowing you down. Because in the old days, you had whoop, things hitting the paper. And if you hit two keys in quick succession, they would sometimes lock and jam. So the whole point of the QWERTY keyboard is to slow you down and to alternate the fingers. Welcome to the 21st century.
Kids definitely don't type with 2 hands. now.
No. And so why do we still have QWERTY keyboards? I want to break out into a song from Fiddler on the Roof.
Tradition?
Tradition, right? We don't love our children. You know, if we did, we would take the hit and learn how to use a new keyboard. But instead, we
Interesting is a lot of the calculators so that they can be used on like SATs
Right.
are in alphabetical order.
yes. And so alphabetical is better, and then professional typists use, I think it's called the Dvorak keyboard. And so if you train yourself, you can actually do better. But this is designed to slow you down and to alternate which fingers you use. But it gets institutionalized. And so frequently we keep doing things where the original reason why we do it is long gone. And we don't even know the reason anymore. Has anybody ever sent an email? Yeah, since you're all supposed to email me, right? And so sometimes you CC somebody. What does CC stand for?
Carbon copy.
Carbon copy. You're carbon copying someone in an email? Some people have changed CC to stand for courtesy copy now, because carbon copy makes absolutely no sense in an email. But things get institutionalized. So one of the things to take away to your students is think about what you're doing and why. So many times, the original reason behind what we're doing is gone. Now, we know how to evaluate polynomials naively. I can't remember, somewhere from the back of the class, there was a good comment about when we were evaluating polynomials, are we doing it from scratch? The way I wrote it, yes, but it need not be. And so if I go back and take the polynomial has so much stuff in it. I assume nobody cares if I do a slightly different polynomial. Let's do f of x is 5x to the fourth minus 6x cubed plus 17x squared minus 11 plus 4. Here is another way to evaluate the polynomial. It's 5x minus 6 times x plus 17 times x minus 11 times x plus 4. And if you look at what happens, the 5x hits x, then hits another x, then hits another x. And that's going to give you a 5x to the fourth. I'll do one more. If you take the negative 6, it's going to hit x, then hit x, then hit x. That's going to give you a negative 6x cubed. This is a great way to evaluate a polynomial. And so this is called Horner's algorithm. And what's great about this is now multiplication is no longer of size or order, d squared over 2, but it's now order d. This might not seem like a big deal if you're dealing with quadratics or cubics, but in the 21st century, we do a tremendous amount of e-commerce. And you need to be able to transmit information securely. So you need to have good encryption. And a lot of the encryption involves looking at huge numbers. And so any savings here is tremendous because the degrees now could be of size 10 to the 200. Well, going from 10 to the 400 to 10 to the 200 is a huge savings. But unfortunately, that's too much for humanity to do. If you imagine the entire universe and try to count how many subatomic doohickey thingamabobbjigs there are, it's less than 10 to the 100. Somewhere between 10 to the 80 and 10 to the 90, depending on who you talk to. Let's just call it 10 to the 100 because that's nice and easy. If every subatomic particle in the universe was a universe, and every subatomic particle in those universe of universes was a supercomputer, that wouldn't be even 10 to the 200. So if you have a universe of supercomputers running since the dawn of time, you're not going to get up to 10 to the 230, for example. That gives you a sense of just how painful these calculations are to do by brute force. If I have to try to do something like this by brute force, it's not happening. And so you said you've heard of Horner's algorithm?
Yeah. My former department head,
Right.
we did at all of our department meetings, he used to bring up either an algorithm or a theorem
Yep.
that aren't commonly mentioned.
Yes.
And this was one of them.
This is absolutely brilliant because it shows you that by rearranging how you do things, you can have a tremendous gain in efficiency. Now, unfortunately, this is not enough for cryptography. And, again, these lectures are carefully prepared over a grueling, 72-hour retreat that I take where I put myself in isolation and plan every moment. How is this related to what we've done before? This is actually related to Newton's method in divide and conquer. So what was the difference between Newton's method and divide and conquer? What did Newton's method assume that divide and conquer did not assume about the function? That you can differentiate. So right now, we're trying to evaluate all possible polynomials. Horner's algorithm is much better, but we can't really do better than Horner. So the question is, maybe if I look at a very special polynomial, I can find something that's better just for those polynomials. And that's the last thing that will finish this unit. This is called fast multiplication or repeated squaring. So if you think of a number, let's say x to the 100, how many multiplications does this cost to calculate x to the 100? 99. So I'm going to show you a faster way to do x to the 100. X times x is x squared. X squared times x squared. X to the fourth times x to the fourth. Eighth. Okay, you give me the next one. What's the next one?
X to the 6th.
No.
Oh, you want me to go X to the 8th?
I want you to go x. See, it wasn't immediately clear.
Yeah.
I have 1, 2, 4. Am I doubling? Am I adding by 2? Well, I start with x to the first, so probably doubling. So x to the 8th is x to the 16. X to the 16, x to the 16 is x to the 32. X to the 32, x to the 32 is x to the 64. Now, 100 is 64 plus 32 plus 4. This is its base 2 expansion. If you look at what we have, x to the 100 is x to the 64, x to the 32, x to the 4. I just have to multiply those 3 numbers. So if I want to calculate x to the 100, I just need 3 multiplications, but I need to compute these numbers beforehand. So I compute all the powers of 2 less than or equal to 100. And then I just multiply the ones I need. What's the worst case for the most multiplications I would need? So here I only had to multiply 3 things on the right side. What would be the worst case?
99 or 100?
Why 99? Well, this is calculating x to the 100.
If you had 100.
Well, but I'm saying for this number, x to the 100, when I looked at its expansion, I had only 3 terms, x to the 64, x to the 32, x to the 4th.
Could the worst case be having to do out the x to the 64th, x to the 32nd, x to the 4th, multiplying those out? So you'd have to do like 2 times 2 times, like, no.
So which number close to 100 would be the worst?
99.
No, because for x to the 99.
64.
Well, if I had x to the 99, 99 would just be x to the 64, x to the 32, and then instead of x to the 4th, I'd have x cubed. So that would just be x squared, x to the 1st. It would be 1 more multiplication.
Oh.
So there's a number close to 100 that has more terms in its base 2 expansion.
96.
Not 96.
127.
127. If I give you x to the 127, that's x to the 64, x to the 32, x to the 16, x to the 8, x to the 4, x squared, x to the 1st. that would mean I'd have to multiply everything on the right. So the worst case is I would have to calculate all the powers of 2, and then I'd have to multiply them all together. But if you're really clever, there's a better way to do x to the 127. You could do it as x to the 128 divided by x. And so depending on how you want to, this then becomes an interesting game about going in both directions. So the cost is at most 2 times the log base 2 of the exponent. That's the worst case. We have to go all the way down and multiply to get the powers of x's, and then go all the way back up. I don't want to go into too much detail. One issue might be how much do you have to store? You know, I now have this table. You can actually do it in a clever way by just keeping track of which x's do you need, that you can keep the storage so you only have to store one thing at a time or 2 things at a time. So you can keep the storage low. Again, if anybody wants to do any of these in their classes, I'm happy to talk to you about subtle points like this. I don't want to go into too much technical detail, as this is now technically the afternoon, right? But I want to give you a sense of, again, this is not using advanced math. This is not using calculus. This is something you can do at an early age. This is one way to talk about the value of doing things in binary. Is I can now do 10 to the 200 very quickly. And computers need to do this if you want to do fast encryption. There's a lot of great things you can talk about World War II. For the planning of D-Day, the code had to be secure for on the order of days, weeks, months. When you're in an actual battle situation, you only need a code that has to be secure for maybe on the order of hours to minutes. Because after an hour, the battlefield situation has changed and it doesn't matter. So you can have a code that could be broken by the enemy that in 4 days, because 4 days is useless. The battle is over by then. So you need to get a sense of how secure must the code be. And all of this stuff comes into play in designing good, fast encryption. And I just love talking about doing things efficiently. Sometimes you need to, sometimes you don't. And it's important to have a sense of when do you have to be clever and careful. If it's something you're doing many times over, then it might be worth learning how to do it well. If it's something that's one and done, you can often, I'm just going to get it done, knock it out, and never worry about it again. With AI able to do a lot of coding, it's really interesting now in terms of how much you need to code, because you can now ask the computer to write some basic code for you, and it will. Okay. Any questions on this before we move to our final unit on games? All right, so let's take just a quick 5-minute break. Stretch.